What if I told you a computer can learn patterns the way you do? By seeing lots of examples and adjusting what it believes. That's deep learning. And at the heart of it are neural networks. Think of a neural network like a giant stack of tiny decision makers. Each one is a simple yes-no, a little or a lot unit, kind of like a dimmer switch. Alone, it's not smart. Stack millions together, connect them in layers, and they can recognize a face, translate a language, or even write this sentence. Here's the gist. You feed numbers in pixels from an image. You feed numbers in sounds from a microphone. You feed numbers in words turned into vectors. Those numbers pass through layers of artificial neurons. Each connection has a weight, a little dial that says how strongly one neuron influences the next. Neurons add things up, push the result through an activation function, like a gate that decides, is this signal strong enough to matter, and pass it on. At the end, the network makes a prediction. Maybe it says, cat with 92% confidence. Was it right? We measure the error with a loss function. Basically, how wrong was that guess? Then we push that error backward through the network, nudging millions of weights a tiny bit to reduce future error. That's backpropagation with gradient descent. Repeat this across thousands, millions, even billions of examples, and the network shapes itself into a powerful pattern recognizer. So why deep? Depth is the number of layers. Each layer learns a different level of abstraction. Early layers in an image model pick up edges. Early layers in an image model pick up blobs. Middle layers learn textures. Middle layers learn parts. Final layers combine those into concepts. Whiskers. Final layers combine those into concepts. Ears. Final layers combine those into concepts. Cat. Different neural nets, different superpowers. Convolutional networks excel at images by scanning for patterns with shared filters. Recurrent networks and LSTMs remember sequences, useful for speech and time series. Transformers look at everything at once using attention, figuring out what matters most in context. Training is the heavy lift. It takes tons of labeled or cleverly unlabeled data. It takes fast hardware like GPUs or TPUs. It takes careful tuning, learning rates, batch sizes, regularization to prevent overfitting. Overfitting is when a model memorizes the training set and fails on new data, like acing the practice test but bombing the real one. Techniques like dropout, techniques like data augmentation, techniques like early stopping help the model generalize. Once trained, inference is the easy part, running the model to make predictions quickly, often on your phone or in the cloud. Why does this work at all? Because the world has structure. Images aren't random noise. Language isn't random words. Neural networks are universal function approximators. They can learn complex mappings from inputs to outputs when given enough data, capacity, and compute. But they're not magic. Garbage in, garbage out. Bias in data can yield biased results, and they don't understand like humans. They model patterns. Still, those patterns can be incredibly useful. Here's a quick mental picture. Imagine a landscape of hills and valleys representing wrongness. The model is a marble rolling downhill, adjusting weights to find a low valley where predictions are less wrong. Not perfect, just better. So deep learning is simple pieces, massively repeated, tuned by feedback. It's how your camera recognizes a smile, how your maps predict traffic, how assistants transcribe your voice. Layers, weights, activations, loss, and lots of examples. From edges to cats, from letters to meaning, from data to decisions. If this clicked for you, here's a challenge. Take one concept, like convolution or attention, and explain it to someone else in 2 sentences. If you can do that, you're already training your own neural network, your brain.